small place.
Oh.
And by
fact that I coordinate my day.
Oh, really?
So if I do
So I said, I was asking you guys
Yeah,
the 28
yeah.
before.
So if I'm viewing
I
this,
because I was
I guess as
Well,
a.
it's a little odd that.
Yeah,
Yeah,
she's the host,
So like-
so
right.
she has to say it's okay first.
Yeah,
So she eyes out in doing
No.
Yeah.
To me, a derivative, it's like a directional derivative. Right, so at the base point, I'll.
She was
in the
actually
direction
coming
of
back when I
matrix
told
B.
her.
Yeah.
So it was like,
I'd do the
you're not
straight
much.
Yeah, yeah.
What do you
yeah.
expect? The kids are in
This is like,
infinitely many
Hey,
things.
Right.
So, you know,
yeah, that's why it's not surprising that the trace is there.
I don't remember, you're also interested.
Yeah, I'll be able to
I
be there. I'll have
I just want to know
Right.
whether
It's a good thing to tell them.
the list, you know.
Yoga kids there.
Hey.
They probably know. It's just like you know that,
Yeah.
Yes.
That just means it's different in geometry. The first assignment was just
Like when I was,
derivatives.
so I told the kids, he said.
Where you are not used to computing derivatives.
Right.
Like at that point in your career.
So I have to
Also,
I think.
yeah, they couldn't determine one another. At that point in your career.
So you put your glass with the one.
And I was like, okay, these are those
Yeah.
Yeah. It looks like a.
Yeah.
Yeah.
Oh, yeah, you go,
And
yeah.
I was like,
So you'll
okay,
feel
you going
those-
for an adventure?
There was a bunch of them. So,
He's like,
still
well,
looking
this
at
thing
the
is
guy.
like such a-
That's when it was like.
Said 3 year
Wow, yeah.
By like the second, it's like to walk. Can I see a picture of the house?
Yeah.
I don't want to do that. Right, like, we're-
Yeah.
Yeah.
You have to kind of deal with this kind of stuff.
Yeah.
So, no, yeah, I still have. Oh, really?
Yeah, especially like, yeah.
One million. See if the kids buy it or not.
Sure, thank you very much.
I mean, cement is hilarious. But I don't know if she would come out of her shell.
Right, yeah.
I
Sure.
think the,
She might.
to me, the, like
not say
the
a word the whole
derivative
time.
Right.
of a function is,
So you never know. And I'm like that too.
it's like it's.
That's why I
it's
say
like
they
terminated
can
Michelle
like
likes
this
to
thing,
Michelle a lot.
and the derivative should
She'll get
be
people out of
bounded
it.
linear map from this
For
state.
sure.
to this.
Oh, well. I'll try hard.
Ah,
Right,
okay, that's,
Maybe I'll-
yeah,
Yeah,
linear. The derivative.
The derivative
is something
has to
which is
be
linear.
at a
when
point, right? If you fix a base point, now the derivative is a linear map, right?
If you come
Oh,
to.
Just like, in calculus one, if I fix the base point, the derivative is a linear map. That kind of best approximates the function you started with at that base point.
Yeah, but other linear thing, so I just want to make things like.
Right, yeah.
It's kind of wins.
It's the only obvious thing, right? Yeah.
Yeah, this probably theorem for the only linear map that does X, Y, Z.
I just looked at this actually. I was looking at the trace.
Yeah.
Clifford
Yeah.
algebra.
Whoa.
And it was the only linear map that satisfies.
Oh, wow.
List of size.
Okay.
I don't have time for that.
But interesting that you
How
say
do they
that.
You're not the only
define
one. You just.
They
yeah.
do it like in a basis free kind of way,
it? Yeah.
right?
Especially
Yeah.
because-
yeah.
I've got a meeting.
Pretty
So
fun.
this you know how to run it, right?
Oh, I know.
Yeah.
It's
all right.
Or should I?
I'm having fun with it right now.
Oh,
probably not.
I thought probably when it's my.
Yeah, I think so.
Yeah. That will work, yeah.
I still was recording.
Yeah.
I think maybe we check that.
Yeah, I didn't.
Oh, yeah.
No, like nothing. We'll see.
You don't count.
Oh, yeah. I mean, if I'm.
Probably try to go to dinner or something one night.
Yeah.
Unless, I guess if I'm super busy.
More space for people.
I don't know which is better.
I don't either. Usually during the week.
But the
rest
of the floor, give you an extension.
Yeah.
You don't.
Get your rules off the table.
I don't think you
Give me an extension.
Okay, so just 5 announcements, actually 2 only. One, coffee will be ready in
Like 5 minutes.
in 5 maybe, so we can make like a very short break for people who run and running. Second thing is, does everybody know each other? This is Mohammad from electric engineer, right? And we check papers. And then otherwise, I think I know everybody, and you can introduce yourself to each other. You have 30 seconds.
30 seconds. Who are you again?
Jersey,
Oh,
like
I
New
see.
Jersey. And all right, so
That was good for introducing you guys. Okay, well, my title is of the talk is Nobel AI, and the reason I call it that because I want to talk about 2 guys who got the Nobel Prize last year, 24, and they work on AI, and just talk about their contribution, but it's not going to be all what they did. It was just the initial contribution which really excited the area of so-called today AI. So I want to talk about the history a little bit and then about these 2 guys. With the history, let's say it will maybe this much time. Trace and then divide into 2. And one guy who got the Nobel Prize in 24 is John Hopfield. And the other guy is Jeffrey E. Hinton. Okay, about the history. Actually, the study, the AI that we know today, really based on the, how the brain works. So it started around 19, I would say 43. Now I need to use my notes. At the University of Chicago. So everything started in Illinois. Let's be proud of that, but I need my glasses. Yeah, these 2 gentlemen, Warren McCullough and Walter 1943, which I wrote there. They started to basically modeling the neurons that they know then, which is still the same model that people use. So
you mean a single neuron?
it's just a single neuron, and they basically say that this neuron have roughly 2 states. One is firing, one is not firing. In other words, active is not active, and active meaning that it sends so many impulses through the axon, very high rate, and that's active. When the rate is not so high, is inactive. And what makes it to be active is all the they call it presynaptic neurons that they basically excite that neuron. And if that neuron is, they call it activation, it goes up to a certain threshold, then it start firing. So this was a very simple model that they had a very simple mathematical model of it that I will talk about it in a minute. And that is still stands. So it started all there, but they didn't know how this such a neuron, which hooks up to another neuron, how does it behave that it gets to us that we think. So it was just a modeling of it, but there was no application, no nothing. But the other people used the idea and came up with the logic gates that we know today, the OR gate, AND gate, binary, and then started the computers that we do know today. And von Neumann John von Neumann was, I think, one of the pioneers to do that. And still the architecture is called von Neumann architecture, computer architecture that we use today, that it has a processor and it has a memory separated from each other. And that computer did computation, and the computation, you write programs, as you know, and it does something for you. And with that, people start having artificial intelligence. They're writing programs that it does, for example, playing chess. So, and one of the guys who helped that was, I think, Shannon. Clyde Shannon was one of them who came up with some algorithm that write this algorithm in a computer, you can play chess with a computer. So it was kind of an intelligent behavior. So I think that was the start of AI, which based on basically rules, right? Certain rules, to do certain tasks, and everything was serial because you would say, if this happened, that happened, this happened, that happened. So it's a serial command of rules that it does something intelligent for you. And that was the AI then. Then with the Macaulay and Pitts neuron didn't get anywhere.
Do we still understand our brain as a processor and a memory separate?
No, it's all convoluted to each other. They're not separated. I will talk about that in a minute. So that's one Neumann machine. So using this really didn't help very much. They call that nowadays threshold logic, because when you reach a threshold, then it does something. But the ordinary logic, Boolean algebra, Boolean logic is 0, 1, and logic gates, OR gate, AND gate, things in that nature, that it does the computation for us. So now the turning point a little bit was a guy named Frank Rosenblatt. I think 19, maybe 40s, I'm not sure. It was right after that, but he came up with a book called Neural Computation or Neural Processor or Neural Processing, something in that nature. And then he came up with the idea of something called perceptron that today even still isn't used. And this perceptron basically came up with the first neural network that we know today. So it has a bunch of neurons that are similar to the Macaulay-Pitts neurons, hooked up in a layer form. So here comes the input to these, and then these neurons hooked up to the neurons on the front, and then it goes to the output. So a neuron like this structure, they call it single layer neuron network, because it has the connections.
Neural net.
A neural net.
Yeah.
Right. It's a single layer because it has only one layer of connections. It has an input layer, output layer. Now, his perceptron actually had another layer on the top of this. So it was really a 2-layer, but the first layer was fixed. And his imagination was, this is the layer that you're born with, which is not trainable. It's fixed. And then the second layer was the one that you train. So his training laws really work for single layer network. And he did not know that if you have more layers, then what would be, the learning laws or learning rules. And so he came up with that. And then he claimed with this structure, you can basically learn any mapping, any input to any output. It's just a claim. And so with that, if you train it right, then you can do basically intelligent thing. And he made a machine, hardware machine to do it.
So this means that
This means that already he thought about training,
Yeah.
Yeah.
He
Like-
started
like
training.
putting
It
weights,
was
and
only
changing the weights. right?
checking the weights, and again, the same thing as Macaulay-Pitts neurons. And now, so everybody was happy, to do this. But again, to build a big one that is really do something useful, it was impossible, right? And a guy, I'm sure some of you know him, Marvin Minsky. He just recently maybe died. He was a guy at MIT, and he started the AI lab at MIT. And he came up with a book called Perceptron. Erase that history portion.
He went to Epstein's land also.
Right, so he came up with a book called Perceptron. I think in 1960, maybe 9 or so, or 8, in that time called Perceptron. And he showed that a simple network, like an exclusive OR, when you want to make exclusive OR, you can make OR gate, AND gate, and things like that with the Rosenblatt with one layer. But if you want to make an exclusive OR gate, you will not be able to do it with one single layer. So it's kind of a counter example that Rosenblatt perceptron is not capable of doing a simple task. And that sort of put a stop on research on the so-called neural net related research to do intelligent things till 1980s. So didn't do much from 60s to 80s. And then the reason was because the AI based on rule-based, they hit the wall. Doing pattern recognition was very difficult to come up with, rule-based algorithm to do a simple, task. So that was one of the things that helps. So in 1980s, I think, in my guess, is that this guy, Hopfield, in 82, he came up with a paper that uses very similar neurons like that, and he came up with a very simple rules that you can do so-called associative memory. And then I'm going to talk about that. And then that actually got something like 30,000 citations so far. So it was really affecting. It was very simple. Even a high school kid can, go through it and then build it. And it does a very interesting, intelligent task like pattern recognition that the AI was not able to do based on rules. So that really excited the area, and everybody uses that. And besides the associative memory, it can also do optimization, minimizes, certain functions that if you map it into a structure, you can use it as that. And it has a very simple electrical engineering implementation of his model that you can do. And one of the things exciting about it is that the system is parallel distributed processing. So it's not like the von Neumann, here you have the processor, here you have that. Everything was distributed, so if you build it in a hardware, it can work much, much faster than ordinary computers. So that was another advantage of this model. And about the same time, about 86, this guy, Hinton, plus 2 other guys, Rumelhart, and so let me write their name. I have to cheat. So these 3 people, they were from University of California, San Diego, and they were in a group, they call it PDP group, Parallel Distributed Processing Group. So, parallel distributed, so that was one of the features of the neural net. And these 3 people, but this one got the Nobel Prize, they came up with the algorithm for perceptron, which can work for many, many layers. not only single layer, it can be multi-layer. And if the number of layers is maybe more than 4 or so, they even call it deep learning. You guys heard of deep learning? That's what it is. It just have so many, maybe hundreds layers involved in that. And they came up with the algorithm to do the training for it that I will talk about in a minute. Now, it was another guy actually in 70s. He came up with the same algorithm, but his name is not so well known. So it was even before the 70s, I'm not sure when, maybe 74 or so. And his name is Paul Werbus. But his area was economics. He did it for another reason. So that's why I think it's not so well known. But in 80s, when a lot of conferences showed up, because there was very excitement about this area, and then started really, so many people got involved with it. And he becomes actually a program manager for NSF on neuroengineering. So that was
No prize, maybe touch up.
yeah, so, and he supported, I think, many neural net related, research and so forth. So that was good starting it. So as you know now, there's so many excitement. Now, if you call AI, it's not the AI of the past, which is rule-based. AI today means neural networks, parallel distributed and all that, and all the algorithm based on somehow. Okay, so let me talk about their contributions. Any question about the history?
So these two guys didn't get Nobel Prize because they lived too short.
Because
He was the first one on the paper age.
An algorithm.
this one got it.
They let the AI thing decide it. Nobody knows why it decided that.
Yeah.
Because only 3 can get them.
And this paper got, I think, something roughly about 50,000 citations.
Oh, wow.
So I think number of citations is one of the key, and also living long enough.
And they bribed the AI bot.
There you go. So this guy is actually 90-some years old, 92. He came to give his talk. He was, with the cane and learning walking, And but anyway, but they really helped the area. Now let's look at their contribution. All right, so Hopfield model is, again, neuron, very similar to the this McCullough-Pitts neuron. And, just showed by a little circle. And there are input coming to it. Let's say X1, X2, and whatever, X of n. And then they put some weights on it. This is a connection that basically controls the behavior of that. Say W1, W2, W sub n. And then the output, let's say, just is equal to Y. Now, this Y could be 1 or 0, active or not active. And if it's just a simple linear sum of the input compared to a threshold, is above or below it. So if, for example, sum of Wi, Xi, I goes from 1 to n, is bigger or sometimes say equal to some threshold, T sub, or just say T. And here otherwise. All right, so this model was what McCullough-Pitts originally proposed. Now, Hopfield did a slight modification, and the modification is that all right, now it's just that equal sign. When it's equal to the threshold, it just does not update the state of that particular neuron. So if I call this a new Y, then this would be equal to the old Y. And then if it's less than the threshold, then it's 0. All right, so we basically evaluate the input coming in, and these X's could be, again, binary, 0, 1, or could be non-binary. And if it's above the threshold, then it sets the state into 1. If it's equal to the threshold, it just doesn't change the state. If it's 1, it stays 1. If it's 0, it stays 0. Does not mess with it. If it's less, then it's 0.
And who gives T value?
It's just a parameter. Now, it depends on what you want to do with the neuron. Then you define the T and the W's.
Oh, okay.
And then it does something for it.
Can we say that this Y is actually a state of that circle?
Yes, it's
Yeah.
a state of the circle of that. And it could be firing. It's like a neuron. So far, same as McCulloch's, except that little deal here. So nothing really exciting. Now, what was exciting, you put them together in a fully connected. So let's say if you have 3 of them, then they are connected like that. So there, everything is connected. And then let's call them like V1 rather than X and Y. There's no input output in a way. So the state of this neuron is V1, this one is V2, this one is V3. And then you have connections like W1, 2, because it goes from 1 to 2. And this would be W2, 2, and so forth. Okay. Then you can define the behavior of this as exactly what I wrote there. So let's say if you have V sub J, one of the neuron, the J's neuron, and his new state is equal to 1 if the sum of Wij, Vi, I goes from, let's say you have n of them, bigger than a certain threshold, Tj. And Vj is old, does not change the state if it's equal, and 0 if it is less than. Now, with that, you can imagine, depending on the values of the constants like W and T, then you can have a behavior of some sort, right? It could have a dynamics, depends on those values. And then he came up with the idea, he called it associative memory.
Xi should be Vi there, or is it? Oh, it is Vi.
It's a V.
It is Vi. So,
Yeah.
Yes. Yeah, and then this is the old, if I may,
Yeah.
go a bit along there. So his idea of associative memory, now I'm going to erase this because now this is what is important.
I want to get a quick question. Do we assume that V is a continuous, the values of V can be continuous?
No, in this case, it's discrete. So it changes.
So,
no,
0 or 1.
Oh, in terms of 0, 1?
No, V is only discrete, right?
Yeah, it's the only one.
Yeah, it is. Yeah.
Yeah, but he has, in 1984, 2 years later, he came up with another paper, he called it a graded neuron. And in that, these are continuous, but again, limited to 0 and 1.
Okay.
So, because the real neuron, they have that tendency, it's not really discrete.
The
And then he
weights-
came up with the model, the dynamics, not as that, but differential equations. So if you guys have time, we can talk about that too. And that one actually has the very interesting electrical circuit implementation.
The weights in the threshold are allowed to be continuous.
What is it?
The weights in the threshold are
Oh,
allowed
yes,
to be continuous.
this and this
Yeah.
is continuous, right? Right, exactly. And then, any negative values too.
Yeah.
So one can think could be discrete between 0 and 1, like every 10th or something, right? The available values for V.
For V,
Yeah.
for this is only 0, 1, but for this
Okay.
graded one, it has a function like that,
Okay.
which goes from 1 to 0. And then, so it was continuous. And then, so that's why we have derivatives and, so to define the dynamics. Okay, so he started this thing called associative memory. It came up with the name, actually relate to something close to computer science called content addressable memory. because you address the memory by its content in a way. And the idea is very interesting. Okay, let's say this has some dynamical behavior. There is a time. And just imagine like a ball rolling down in some sort of a potential value as a dynamics. So we look at the dynamics of this ball. And as you see here, if the ball is here, where is going to end up? Right here, right? Eventually, right? It just goes on. Maybe if there's some friction or so forth, eventually it would end up here. And if the ball is here, would also end up there. But if the ball is here, it would end up here, and so forth. Okay, so what's that? So these are so-called equilibrium state of this dynamical system defines what you storing. So what is stored is these points. Now, this is one-dimensional. Now, again, this is continuous, but this is discrete. But to just give you an idea that, what he meant by that is that defining these W's and T's in such a way that the dynamics of this model would be stable. All right, now this stability goes to some stable fixed point. Say this or that. And what these stable states are resembling is what you are really memorizing. Now, how do you recall what you have memorized? Is by these initial states, which are near what you have stored. For example, let's say if you store the dictionary, right? You give a word that is misspelled, is near one of the words that you have stored. So what happens in this model? It just brings up the corrected word, which is near the one that you misspelled. Or it could be, let's say, think of it as a picture. You store a face of somebody, and this one is related to maybe, mountains or something. So you give the face, not exactly what is being stored, but maybe a distorted version or another version of it, or maybe missing something. Then it goes to what you have stored. So this way you can use it as a recognition system. And, same thing here. Could be, mountains, and then you give us something which shows them mountain. And then
Mount Rushmore would be a problem.
What is it?
Mount Rushmore would be a problem.
Yeah, I'm sure that there are many problems. Now, the good thing about this model, think of it, which is very interesting, is that recalling the information is independent of how much you have stored. Because recalling the information just depends on how far you are from what you have stored. And he thinks that this is the way maybe our brain stores information. Because we recall things very fast. It doesn't matter, how much we know, it doesn't get slower, right? But with a conventional system that, the more you store, the slower it gets, right? Because he has to sit through so many information to dig that out. But the search is very local. So that was very interesting about his dynamics. Okay, now let's see how this associative memory works. So this was the idea. All right, so let's say you want to store something, these guys, as a vector. So just imagine we think of this as a vector, and I just put, usually, this is again from his original paper, we put a superscript for the one that we want to store. So these are constants, things that you want to store. And let's say, just make an example too. Let's say 1, 0, 1, 0. So so let's say we have 4 neurons, and the state of the first one, 1, second, 0, and so forth. This is what we want to store, and this is, let's say, this picture here. Right? You can always, sample the pictures into so many bits, right? So many pixels, and then the pixel represents a vector. Now this vector could be really a high dimensional. So then let's say store another vector. And he came up with the formula. Now he didn't really show any proof of the formula, just state the formula. And the formula is that we choose T, J all equal to 0. So the thresholds are all 0 chosen for its case. And the Wij, the weights are equal to summation of 2V I. Put a super S, and I'm just describing what that means. I mean, in this case, it goes to 2. And we force the diagonal of this matrix equal to 0. See, this weight is going to be a matrix, right? In this case, 4 by 4. And this is the formulation that we are using to store these two vectors. All right, now these two can go up to anything that you want to store.
Did you
already
tell us what S represents?
S is just a superscript for that.
For the
Two vectors, one or two.
Yes, let's say 1 and then 2.
Okay.
Okay, so let me work this out. All right, so doing this is easier to represent it by an utter product. So let's say the first one is going to be, now with this equation, you see if it's 0, it becomes -1. If it's 1, it becomes 1. So wherever I see 0, I turn it into -1. Right, so what I did here is exactly what this represents, utter product formulation. So that's for the first one plus the second one. All right, so again, these are the elements of that matrix. So this will give you 1 minus 1, 1 minus 1. Diagonal, usually we get the number of things we want to store, but we force it to 0. Again, that's his algorithm. All right, so it's going to be 2 actually. So the next one is
Yeah, they're all 2. Is that
0, right? I mean, the next element was 0, then the next one is 2. Is that right?
Negative.
-2. Now, if you look, the matrix is symmetric. I'm going to intrude into Hinton's area. Okay, so this probably would be that. And then here's the next one is 0. I mean, it's 2 actually, but we'll force it to 0. The next one is 0, right? Next one is 0. This one is 0, right? And then next one is 2.
And then
This
-2.
one is -2.
Yeah, you can see better because of the
And
distance.
then this is 2, and then this would be 0, and this would be -2, right? And then we force these to be 0. Or we can say -3, or in this case 2, times the identity matrix, But All right, so this is the connection. So in other words, if you want to store these two vectors, the structure that you have would have these connections. So what it says the actually there is no self connections. So the first one, the next one is no connection. The first one to the second one, there's a connection. So let's say this is the V1, V2, V3, and V4. So first one to the third one, right? There's 2, and since it's symmetric, then this would be also 2, right? And then to the fourth one would be -2, and this would be -2. And now here would be all 0, meaning that 2 is just hanging there, doing nothing. So 2 is not used in this example. And the third one to the first one, which we already did, and then the third one to the second one, with no connections, and that's clear, no connection. Then with the fourth one, there is a -2, right? And then the fourth one to that is also -2. So this is kind of a drawing of what Hopfield is proposing. If you want to store these two as stable state of this architecture.
So is the assertion if you start V1 through V4 with any state and run the dynamics, you will land on one of those?
Exactly. That's the hope.
Yeah.
Oh, well, that's the hope, but
It's hope field.
is a hope is a field of hope. Now it works when you have many neurons. See, this is a simple tool. I'm not sure if it does or if it doesn't. So what I'm going to do, use that, let's say this or this one as an initial state. And if it's stable, it should not change, right? So let's do that.
So V2 never changes. The other 3 components are the same. So it could work.
Yeah, you already figured it out.
I think you don't have to take final.
Yeah, so there you go. So to do
It
it,
does seem like you're storing 4 pieces of information in a 16-piece matrix.
right. So
Not really, right? It's
I
you
erased
can
it.
forget the main diagram.
What was it?
Okay.
0.
Yeah.
You guys remember that? I erased it.
Well, we could get it
Zero.
back.
So in rows, 0, 0, 2, -2. 0, 0, 0, 0. No. I'm rows.
Rows.
Okay.
The second row, 0,
0, 0, 0, and this one it's
2, 0, 2, -2.
2, 0,
0.
2, -2,
And then -2, 0, -2, 2.
and
0, 0.
This is 0, right? So this was the one, right?
Mhm.
Okay, so to do the dynamics is the simplest way is that matrix multiplied by the vector. Vector would be the initial state. So let's pick the first one. Okay, now to run it, there are 2 ways to do it. One, so-called synchronous, meaning that you multiply this, but you don't change the state. You figure out what that summation would be, and then you compare it to the threshold, and then you update all the state at the same time. So that would be synchronous. Now, what should work for stability, there's the proof for it. It should run as asynchronous, meaning that you update one neuron at a time, rather than update all of them at the same time. So let's say starting, and it doesn't matter, you can start maybe randomly. You can start from the first neuron. So we multiply this with that, so we do the summation basically. Right?
You get 2.
So what do we get? We get 2.
2, 0, 2, 0.
All right, so 2, the threshold is always 0. The T is always 0. So 2
We'll turn into
is
1.
above, so it's becoming 1. All right, so that didn't change. That's good. The next one, since it's all 0, doesn't matter what's going on. You get 0, 0 is the threshold, so you do not change the state. If it's 0, it stays as 0, right? The next one, 2, 2 and 0, so we get 2, right? And 2 again above the threshold, 1, and the last one, -2, -4, right? And 0. You see, it did not change. So this was a stable. Now, if I try the next one, maybe I get a stable 2. Now, it may have some other ones that are also stable.
Like 0.
Yeah, like 0. If you put 0, 0, you get nothing changed. So 0 for sure is a stable. And also the complement of this should be a stable too. The reason is because this formulation does not know the difference. If you look at if you put the complement of what you put in, you get the same formulation. So the complement should be also there. So again, this would work. So the excitement was very simple, right? To write the algorithm. And then, you can have vectors which are huge, representing images, pictures. And since it's huge, then it tends to be working. So a lot of people use that to write papers because it's simple, innovative, and it can do pattern recognition that, is not easy to do with the AI, so-called then rule-based, type algorithms. And so simple as this. Now, this also could be used for optimization. This formulation or dynamics that I just, showed you, what we did here as things change, and it goes to a stable state. And if you have an optimization function, some function that you want to optimize, if you map it into is so-called energy function, this from dynamical system, Lyapunov function that, as the dynamics, works, this function basically minimizes if it's stable. And and again, this was Hopfield contribution. His so-called energy function was given as this. So choosing, now this is general, it's not the associative memory. So we have a Tj, which is not 0, and also Wij. And he shows that the dynamics of the system is always stable if you choose Wij equal to Wji. So if you use the symmetric weights, doesn't matter what the others ones are, this is always stable. So it always goes to some stable state. Now, if you have a optimization function problem, then if you map it into this, how do you map it? Choosing Ti and Wij. Then you can use his architecture to optimize your problem.
This looks like kinetic energy and potential energy.
Yeah, could be. Right. So now I have an example, but I think I haven't talked about this guy yet, of an application that he put into his paper of 84 that you can do an A to D converter. A to D converter, analog to digital converter, using his idea of basically mapping the two together. So I think I stopped on his, but that was his main contribution, associative memory and a simple algorithm right there that it can store vectors as a stable state.
So if you started with 0, 0, 1, 0, so the hope is that you will restore V1, right? Because it is closer to V1.
Now, if you, for example, change one of these, and then hoping it goes back to this. Yeah, that is the,
yeah, but
so that would be
0, 0, 1, 0.
0, 0,
1, 0.
So you just change that to 0 and see what happens.
And this one will be, yeah, so it's farther. So like, yeah, okay.
So what happens?
Oh, you don't have to calculate, but it's just
So, like,
Yeah, but,
intuition.
but that's the idea, but it may not, it
Yeah,
may
yeah.
go to that.
These are pretty close together to begin with, so.
So pretty much like coding theory, right?
Yeah, like a Hamming distance, so-called, if it's smaller, then, it should approach whatever that is closer to.
Error correcting code could be an application.
Yeah, that could be right. So this is what Hopfield did.
By the way, so if Jackson allows, do you want to take another day?
I was gonna offer it. I'd love to see more of this.
Yeah, so
Yeah,
you don't rush. So can you take it the next week also?
Yeah, I can talk about this one maybe next week, and I
Okay.
can talk about this one on the A to D converter maybe.
Yeah, okay.
Is there any meaning associated with unstable points and saddle points in this?
Well, he is talking about stable state. He never discusses anything besides that. So it could, Now, this was the initial, finding of his, but people have worked on this, they have bidirectional associated memory and so many other things that I'm sure it can go to some other dynamics besides just a stable state. But stable state may be not so interesting if you want to do something interesting, because it just goes to something and doesn't change. But if you want to map it into something which changes all the time, right, or mimicking something which changes all the time, then this would not be applicable. But people have worked on that. So this is just an initial 1982 of Hopfield that I think started many things. You have 30,000 citations.
Okay.
I'll make one comment mainly for the undergraduates here.
Mhm.
So Professor Ming-Ching Xiao had an honors course on the history of machine learning
Okay.
last year. I don't know if he's doing it again or he's doing it in the future or not, but you might keep an eye open for that if that interests you.
Yeah, if there's any interest, there are many.
Go upstairs to physics department, they have time machine.
But he may have notes. I've read a couple books on this. I don't remember, but-
So here you apply this matrix with this funny multiplication, let's say only once. Can you repeat it again? in case-
Yeah, this is only to
Just one step.
just one step, right?
Okay.
Then if it's a stable, then doesn't mean to go any further.
Yeah, so normally. we
But if
just
it
repeat
doesn't, then
repeat
you
repeat
just
it.
keep
So
on
this-
going till it goes to some stable.
So this is
And
dynamic.
hoping that these
Yeah,
two are the
okay.
only stable state. But
Looks like Markov chain, but not exactly Markov.
no Markov chain.
So the
Yeah,
primary
it's like Markov chain because there are connections between units.
input is the Wij, that is the primary model there.
This one is
Yeah,
what?
that is that the most important part here? Input?
Yeah, this is his contribution because the rest, nothing, McCulloch's already had it. But this was his contribution.
And now it has
Choose-
changed.
If you choose that, then you can store things.
So this W should be really H.
Hmm?
The W should be really H, right?
You should be H.
Yeah, hope you.
Oh, well, no, because it was a weight. They used it in
I know.
the
Yeah,
weight
yeah,
connection, strength of.
So is this what
Synaptic
people try to
connection.
change?
Hmm?
Is this what people try to change if you want to modify these things?
Yeah, this is the programming. This is really the programming of this. How you program. See, this is exactly what you said, distribution. The memory and process not separated because memory is these, right? And the threshold is the memory. And the processing is all of these things that is doing. So they're not, separated. No
Is
question.
it being categorized categorically
But
from a categorical point of view? Has it been categorized like that
Categorized.
diagram?
yeah, those are categories of, you can imagine as that.
So that diagram seems to can be understood from Petri nets, open Petri nets.
Yeah,
But it has
Petri nets,
transition.
yes.
Is
These
it
are
you
computer
can-
science related stuff. Yes, these are very similarities. But Petri net didn't have that much of a use. I don't think they had that many citations. Yes.
Petri nets deal with discrete dynamical system.
Yes.
So you use it to deal when you have a big, like lots of these diagrams where then you can decompose them together
Yeah, I'm sure this can be mapped into a Petri net.
and then
Yeah.
over there they use, for example,
Definitely.
Julia algebra for
That's
the
right.
programming. So
That's
what kind of program do they use here? Because you talked about
This one, you can write any code you like. I mean, people, use MATLAB, they use Python, they use anything that you can do computation, because this is the computation, it's just the multiplication and summation, and then thresholding, right? That's all there is to it. So you can do it with any, anything. But the one which is continuous, the graded neurons, you could do it in a hardware. So it's not really computer.
Analog.
Yeah, analog, right, exactly. So I can maybe talk about that for the 5 minutes. Now, his computational model is actually, it's very easy to show with electrical stuff.
So in top field or?
Yeah, this one.
Yeah, okay.
Yeah, I'm going to. This one is gone. Actually, I'll just quickly. Okay, this is a simple model of the neuron electrically. Now, let's see what does it mean. All right, so here, a little bit of electrical engineering stuff. I'm sure you guys know Ohm's law, right? V is equal to R times I. And then extended Ohm's law for the capacitor. C, the voltage equals to V, the current through I is for that. And for the capacitor is, what is it? I is equal to C times dV dt. So this is all we need. And then these guys, they call it usually high amplification op-amp, the operational amplifier. And what it does, it basically does the thresholding for you. So here's the input, let's say the voltage is U, the output is V, and relation is that it does this for you. The thresholding. So basically, this is what this op-amp does. High gain op-amp. So it saturates and then it goes to some values. Let's call it 1 and 0, and that's what it does. Now, to figure out what this network is doing, is that the current coming to this node should add up to 0. They call it like Kirchhoff's current law. So it's a very intuitive, right? All the water pipe coming in, if you add up, you should get 0, right? In all directions. Like 2 going this way, then it must go that way. So this is negative, these 2 are positive, then it adds up to 0. So now the current coming in this direction, the Ohm's law, the voltage here minus the voltage there is U. So what you would get, the current flowing this way would be minus U divided by R. The current going that way would be, this one here would be minus C du dt. And then the current, now op-amp is a very high impedance, so no current flows into them. So no current coming. Now the only current left is right through here, which depends on the input to that neuron. And let's say there's another neuron just like that, and then it's hooked up to this through a resistor. And that resistor, let's say, is R21. So it's coming from the neuron 2 to neuron 1. And now the current coming through that would be the voltage here, which is coming from the other neuron. Let's call that V1, the other one would be V2. So it's going to be plus V2, that guy, and here's let's call it U1, right? The voltage here, and then divided by R21 equal to 0. So this is the Kirchhoff's current law for that node. Now, to rewrite this equation, we get du dt, let's say, equal to minus u divided by RC. I divided already by C. And then on the other side, what do we get? We get V2 divided by R21. And then we have that C there, right?
It should be a plus on that though, right?
It should be a plus, right? And then minus U1 over C R21, right? Something like that. Okay, now this is only I wrote it for 2. Now, if this dynamic goes to a stable state, this becomes 0, right? And then what we got here, if you figure this out for V, what happened to V1? Yeah, I just wrote it for connecting to only V2 neuron. So what we get okay, we get, let's call that U1, right? And so what we have U1
Maybe you can use
equal
amplification.
to, right?
V1 over
Or let me 1 over RC plus 1 over R21C, right? Equal to
V2 over C R21.
V2 over C R21, right? That happens at the initial state, and let's see. Well, it's not easy to relate to what I talked about. Let me,
Intuitively, where is the memory sitting in
no,
the
no, no.
capacitor?
Let me make it into more units, then I think becomes more clear.
Okay.
Right now, all we have is
Yeah,
it doesn't have the see, it could have a self connection where the V1 comes in, through another resistance. So let me write the if you have many, this dynamic system is going to be something like that. This is what will happen. The equation that I wrote, if you consolidate those resistances into tau and then those other resistances into Wij. So I need to draw more to become more clear. Things were missing. It was only a connection from the second neuron, so some of the thing was missing. So when dynamics become stable, this becomes 0. Then here this U of J becomes equal to tau summation of Wi on. And that's exactly what we were, right? This is the summation, and this is what we get. And the Vj is equal to F of U I, right? So, and this is the Uj which goes there, and then the output of that. So let's say if this is J and this is J, and that relates to the thresholding. So the output becomes either almost 0 or 1, representing the Hopfield network. And the dynamics is exactly the equation of the Hopfield, right? Because this is the summation that we had. The only difference is it has that constant tau, and a constant does not, if it's a positive constant, does not change the dynamics. So in that sense, we have the same behavior as the discrete Hopf field, but is in the form of a continuous variable, and it has a nice electric circuit implementation, which is, and then they're all hooked up together in a parallel processing, so it can work very fast. And then if you program it, choose the WIJ and so forth, then you get the dynamics that you are looking for, just like the one we just talked about. Okay.
So did Hopfield make that?
Yes, this is,
he did.
they came up with that in the 84 paper,
Oh, okay.
and they call it graded neuron.
Can you send that?
Yeah, I can send it to you. And the other, I think, applications, they came with the Hopfield and Tank is another guy they put together. Another paper. Okay, so that's it. Thank you very much. So I'll talk about the Hinton.
Yeah, right. So with one visit to Radio Shack, you can actually be the one in your kitchen, right?
But there is no radio
Radio
shack.
Shack.
That is the problem. They used to.
If anyone wants coffee, the coffee should be ready by now.
If you remember.
I hope.
Nice.
You remember
So
this.
it's the part of that.
Yeah, that's not.
Yeah,
So
the
this
coke
is
factory.
the derivative at A of the determinant.
Something to that.
That
So the coke factory.
Yeah, yeah. So yeah, I'm wondering if what you're writing depends on the fact that you have like
Am I supposed to understand that?
A minus xi in the argument.
Yeah.
Right? I think that this is just the determinant of A. But the derivative of the determinant. Yeah.
Thank you.
Right. But you don't
Yeah, I mean,
Maybe 2010.
There's gonna be on top of the
Like,
yeah, I mean, it's hard. All of us know it.
Yeah. So
Well, interesting. I speak to
Kind of bow out.
it's a little bit.
It would be a very weak AI.
Yeah, I can. However you want to do
You
that.
have to kind of.
even if it's full.
It feels up to
Thing, you're trying to
But
remember your word.
But
your
it
name,
goes and so
I know his name.
I think they made it
always the same state.
That's the voltage here.
Right.
The state of the.
this thing
Yeah,
here.
it's really
Stability failed this
More
time.
the best way to present it. So
You can know that
there's various.
You can buy it.
Oh, they're cheap.
Very
This is interesting.
we just learned it in the.
The chip itself is like 6.
It's like the slow.
Like if you buy it,
Slow approaches. Like
Alibaba, maybe.
First one did that.
They both approach things.
Thank you.
Here, what you think?
Yeah.
So,
The other one, because it relates to
Similar one.
this one, we historical.